what should be the condition? It has to be a bijection. Otherwise, what will happen? If it is not a bijection, then what will happen? See, for this element, say x1 and x2, these two elements are going to the same image. Okay. For the inverse, what I need, if I want to define some inverse, this particular element should go back to the original position. So only then the inverse will be meaningful. Right? Two different elements, they go to the same image. Then what will happen? What will be the original position of y? There will be two different original positions of y. Okay. So that will create a that will not allow us to define inverse, because for the reverse one, this particular element will have two different images. Okay. So the function has to be 1, 1. It cannot be, if the function is not 1, 1, then we will get this type of problem. A particular element may be assigned to two different elements. So that will not allow us to make the inverse function. Okay. So first it has to be 1, 1. Okay, 1, 1 will do. So but not only 1, 1, if there are some extra elements here. Okay. If there are these elements which do not have any pre-image, that will also not allow us to define a function, because for definition of a function from y to x, what do I need? I have to get an image for every element. For every element in y, I have to assign some image. Okay. So if these elements are extra, they do not have any pre-image, so it's difficult to assign the image. Okay. So that will also not allow us to define an inverse function. Okay. So it has to be actually 1, 1 also, 1, 2 also. For every element here, it should have some pre-image. Okay. So from the diagram, we have an idea that for inverse of a function, the function has to be a bijection. Okay. Otherwise, it's not possible to define the inverse. Okay. So let us see how we define the inverse of a function. Okay. So for example, you have something like f from r plus to r plus. R plus to r plus, and there is f of x equal to say 1 by x. Okay. From the set of positive real numbers to the set of positive real numbers. Okay. F of x equal to 1 by x. Okay. Or just let me write fx equal to twice x. So the element x goes to its image twice x. Okay. Under the inverse function, what should happen? This element should go back to its pre-image. Okay, pre-image is equal. So if I denote the inverse function as say g, what should be the image of this twice x? If g is the inverse function, then g of twice x has to be x. Okay, this is the intuition behind inverse functions. Okay, I want to define the function in such a way that the image of this element in the range, okay, is actually the pre-image under the original function. Okay, I want to define a new function where image of each element here is actually the pre-image of that element with respect to the original function. Okay, that is how we define it. So if I take an element y from there, what should be g of y? The inverse function g of y should be what? Just if you have a look at this. Or if I take an element x here, what should be the inverse image of that? It should be something like x by 2. Okay, right? So, and if I take GOF of x, what will be this one? G of fx. So what is fx? Fx is twice x, and g of twice x is again x. So this should give us the identity function. So GOF should give us the identity function. What is FOG of x? This will be f of gx. So this will be f of gx is what? X by 2. Okay. And what is f of x by 2? It is twice x by 2. So this should also give us the identity function. Okay. Only then we can our inverse will be meaningful. So GOF and FOG both should give us the identity function. Okay. Only then the inverse is meaningful. Okay. So it's something like reciprocal. So if you have a real number, positive real number, this not only positive, non-zero real number, then what is its reciprocal? Will be 1 by x. No? And what is the property they satisfy? If you multiply a number with its reciprocal, you should get the identity element, multiplicative identity. Okay. So it's something similar, right? Means after composing G with F, I should get the identity function. Okay. After composing F with G, I should also get the identity function. Okay. So that way we will define the inverse. Clear? So let us write this definition. So let F from x to y be a bijection. Then we can define the inverse this way. So let F from x to y be a bijection. Okay, be a bijection. So then inverse. So we'll write the inverse later. An inverse of F is a map. G from from y to x. Such that define such that if f of x is y, then so this g is defined with the help of f. Okay. So whenever we have an element x which satisfies fx equal to y, then your g of y should be equal to x. Okay. So just the pre-image. Image of x is y under f. So under the inverse map, image of y should be x. Okay. So that is how it is defined. Okay. So the function itself is defined using the help of the original function. Okay. So original function is f. Okay. So each element in y actually goes to its pre-image. Okay. Every element in y goes to its pre-image. Okay. And because it is a bijection, the pre-image is actually unique. Okay. Since it's a bijection, so it's a 1-1-1-2 map. Okay. So there cannot be two different pre-images. Okay. Since it is 1-1, so if I have an element y here, it cannot go to two different images. Okay. Because in that case, f of x1 equal to f of x2, this will mean that x1 is actually equal to x2. So these two elements are actually equal. Okay. So because it is a 1-1 map, we could define like this. Otherwise, it's not possible. Okay. Right. So it is defined as this way. Okay. So one thing we can see that there is only one map which can be defined this way. Okay. So there cannot be two different functions which satisfy the same. Okay. So if note that if G and H are two inverses of a function f. Okay, of a function f. Okay, then what should happen? G should be actually equal to H. Okay, we will show this how it is. Okay, so that's actually obvious from the definition. If you have two functions, suppose you come up with a function g which satisfies this, and another one comes out with a function h which satisfies the same condition, then actually this g and h should be same. Okay, they should be same, right? So we have, so let y belongs to capital Y. Okay. Then since f is a bijection, in f from x to y is onto. Okay. So it's a bijection, so it's onto. So there exists x in capital X such that fx is y. Okay. So by definition of inverse, we have fx to the y one. If fx is y, then what is g of y? G of y will be x. Okay. By definition of inverse, g of y is x, and h is also in inverse, so h of y is also x. So from these two, what I get? Therefore, g of y is same as h of y. Okay. So y is an arbitrary element. So g and h, they agree on arbitrary elements. So g and h are actually equal. Okay. Which one is that? Just follows from definition. You take an arbitrary element y inside capital Y. Then since this is a bijection, so it's onto, so there is an element x in x which satisfies fx equal to y. But if we go by the definition of inverse is defined this way: whenever fx is y, g of y has to be x. Okay. So since g and h are both inverses, so we have g of y is x, h of y is also x. Okay. So if you combine these two, we have g of y is h of y. Okay. So that's ultimately what I have got. Thus we have got g of y is equal to h of y for all y inside capital Y. Okay. So that means g and h are equal. So the inverse that we define this way is unique. There is only one function which satisfies this. Okay. Right. So it's obvious actually. What we are doing is we are just taking the opposite direction. Okay. So this is x, this is y. X is going to this, this is going to this, this is going to this, this is going to this. Under the inverse, what we do? This goes to this, second one goes to this, third one goes to this, fourth one goes to this. Right? Okay. So only one function is there, which is defined. So inverse is uniqueness of inverse. Okay, so we will denote this unique function by f inverse. The unique function here is defined as f inverse. Okay. Thus, the inverse of a bijection f from x to y is denoted by this symbol. We denote it by this symbol, f inverse from y to x. Inverse from y to x. So for example, if you have a function from this to this, say 1, 2, 3 to the set 5, 7, 8. Okay. So defined by say f of 1 is 5, f of 2 is say 8, and f of 3 is 7. Okay. Then what is f inverse? F inverse from 5, 7, 8 to 1, 2, 3. Okay. 3 is defined as what? What will be f inverse of 5? F inverse of 5 क्या होगा? 1. F of 1 is 5, so f inverse of 5 is 1. F inverse of 7 will be equal to 3. F of 3 is 7, so f inverse of 7 is 3. And f inverse of 8 will be 2. F inverse of 8. So this is how we define inverse. Okay. Let's take the P inverse. F inverse of 7 is 3. F of 3 is 7. So the inverse of 7 will be defined as its pre-image. Every element goes to its pre-image. F of 2 is 8. So F inverse of 8 will be this 2. Okay, that is the definition of it.
F of 2 7 will.
Correct.
F of 1 5.
Right. This is one function. How many functions are possible? The first class I told you. How many functions are possible from here to here? 27 functions are possible. Okay, I have defined a function like this. 1 goes to 5, 5 goes to 3. If you define the function this way, okay, विभिन्न रकम function define.
सर ऐसा नहीं होगा ना, सीरियल वाइज
नहीं होगा. Serial wise नहीं भी हो सकता है. There are 6 functions, 6 permutations here. There are in total 27 functions. And out of them there are 6 bijective functions. Okay. So if I have a function like this, f of 1 is 5, f of 2 is 5, and f of 3 is 5. Okay. Then what is the inverse? This inverse doesn't exist because the function is not a bijection. No? It's not 1, 1. Okay. So in that case, what will be the f inverse 5? We cannot say. Okay. This 5, its pre-image is 1 also, its pre-image is 2 also, 3 also. Okay. I need a unique pre-image. Okay. So if the function is not 1, 1, I cannot define it. Okay. Now if you define the function something like this, f of 1 is 5, f of 2 is 7, f of 3 is 8. If you define the function this way, then f inverse 5 is 1, then f inverse 7 is 2, and f inverse 8 is 3. Okay. So you can define it in several ways. If you define another function something like g of 1 is 8, g of 2 is 5, and g of 3 is 7. Okay. In that case, what is g inverse? G inverse of 5 will be 2. Okay. G inverse of 7 will be 3. Okay. And g inverse of 8 will be 1. Okay. So under the inverse map, each element actually goes to its pre-image under the original map. Okay. So this is what is happening. Return आगे discuss कर लम्बे नहीं पर्सन একটু ডিসকাস করছিলাম কোরিয়া করছিলাম একটা ভিডিও আপলোড করব আমি ওটা দেখিলি আপলোড করছিলাম দেখছো না ভিডিওটা ওকে देयर इज अ वीडियो इन दिस गूगल क्लासरूम यू सी ये functions introduction to functions ওটার মধ্যে explanation আছে and this explanation is very simple you have already done in your this permutation combination chapter in higher secondary first year long time back 2 years back no so say I have something like a1 a2 up to an okay this is a set having n elements okay and this is a set having say 1 2 3 3 elements. Okay, so how many functions can you define from this set to this set? Okay, how many functions can be defined? How many functions can be defined? Defined from A to B. So only for finite sets we can say this. For infinite sets we cannot say how many. Okay, there are many, infinitely many. So how many functions can be defined? Just concentrate on the multiplication rule of counting, okay, which you have done in permutation combination chapter. Okay. मने ऐसे suppose from Silchar to Guwahati, okay. So there are Silchar to Guwahati to Kolkata. Okay. So suppose there are 2 ways or 3 ways, 3 ways to go from Silchar to Guwahati. Okay. And there are 2 ways to go from Guwahati to Kolkata. Okay. Then in how many ways can you go from Silchar to Kolkata? In how many ways can you go from here to there? So this is the first example in your permutation combination chapter. 6 ways. That is the fundamental principle of counting. Okay. Or actually it is called multiplication rule. Okay. If a task can be done in say n ways, and for each way of doing this task there are p ways of doing another task. Okay. For each way of doing this task, okay, there are p ways of doing another task. Then both the tasks can be done in n into p. Okay. So here there are 3 ways by which you can go from Silchar to Guwahati. So if I take this route, say bus, okay, then I have 2 options from Guwahati to Kolkata. Okay. So suppose I go by bus, then again there are 2 options available to us. Okay. Suppose I go by train from Silchar to Guwahati, then also 2 options are available from Guwahati to Kolkata. Okay. And if I go by flight from Silchar to Guwahati, then also 2 options are available. Okay, so how many options? Do choice. Okay, 3 into 2. Okay. So exactly that principle is applied here. So finding a function from A to B is equivalent to placing these elements somewhere. Okay. So the image of first element can be chosen in how many ways? F of 1 can be chosen in how many ways? 3 ways. Okay. So f of 1, this can be chosen in 3 ways. Okay. Any one of them, right? Sorry, f of a1, f of a2, this also can be chosen in 3 ways. F of a3, this also can be chosen in 3 ways. Okay. Similarly, f of an can be chosen in 3 ways. So images of all these elements can be chosen in how many ways? 3 into 3 into 3 into 3. How many times? N times. So the number of functions is actually 3 to the power n. Only the fundamental principle of counting. Multiplication.
Sir, if the sentence of that, suppose A the infinite number of elements is there.
So infinite actually we cannot say exactly how many. Infinite actually there will be infinitely many functions. Okay.
Suppose sir n times elements is there. And n to the 3 times.
Also same system. Suppose you have a1, a2 up to an here. Okay. And here you have b1, b2 up to bm. Okay. So the image of first element can be chosen in m ways. Image of the second element can be chosen in m ways. Okay. So m into m into m into n times. Okay. So this is actually m to the power n. Okay. So number of functions from a set having n elements to a set having m elements is actually m to the power n. Okay. So out of these functions, there may be some functions which are 1 1. There may be some functions which are 1. Okay. So functions which are 1 1, that also we can find out. Okay. How many functions will be 1 1 from here to here? 1 1 provided For one function, I need n should be less than or equal to n. So how many functions will be For one function, the first element can be mapped in m ways. Okay. The second element can be mapped in how many ways? M minus 1, because the function has to be 1 1. So the image of a1 that I have chosen is blocked. Okay, we cannot choose the image of a1 again. Okay, so for the image of a2 there are less options, m minus 1 options. For the image of a3 there are m minus 2 options. Okay, like that. So for the image of an there are how many options? M minus n plus 1, m minus n plus 1. Okay, so this you can easily see, it's factorial m divided by factorial m minus n. Okay, so it's actually mpn, number of permutations of m objects taken n at a time. Okay, that is so number of one function it's very simple, but number of onto functions is very difficult. Okay, not very difficult, but still very difficult. Okay, so for that example, আমি যেটা ভিডিও দিছি ওটার মধ্যে আছে দেখো inclusion exclusion principle. Okay, for finding out the number of one function onto function. Okay. This problem, how many ways can you distribute say 12 balloons of different colors. So balloons are usually non-identical. Balloons of different colors. To 10 children. How many ways can you distribute 12 balloons of different colors to 10 children? Simple problem, na? Nah, 12 meter. You can distribute in many different ways. Okay, so this is actually finding out the number of functions from a set having 12 elements to a set having 10 elements. Okay. There are 12 balloons, B1, B2 up to B12. Okay. And there are 10 children, C1, C2 up to C10. Okay. So it may happen that you can distribute all balloons to the same child. Others will try. Okay, it may happen. It may happen that you distribute balloons to different children. Okay, so actually we are finding out functions from this set to this set. Okay. So how many ways can you distribute? 10 to the power? Okay. This many ways. Okay. 10 to the power 12 ways. Because the balloons are non-identical. Distributing balloons is equivalent to finding a function from this set to this set. That is what you have to understand next. Okay. Distributing balloons is equivalent to finding a function from this set to this set. How? See, suppose you reduce the number. Suppose there are only 3 balloons. Okay. And there are suppose 2 children. Okay. So it may happen that you give all balloons to this child. Okay. It may also happen that you give all balloons to this second child. Okay. Or it may happen that you give 2 balloons to this child and the third balloon to a different one. Okay. This is another possibility. Another possibility is you give B1 and B3 to C1 and B2 to C2. So actually what we are doing, we are just constructing a function from B1, B2, B3 to C1 and C2. Okay. So if there are 3 elements here and 3 balloons here and 2 children here, then you can distribute it in 2 cube, 8 ways. Okay. 8 भागे distribute करते हैं. Okay, so this problem is simple, but this will become very difficult when we include another part. Another part is this. How many ways can you distribute 12 balloons of different colors to 10 children such that each child gets at least this one value. One problem ta kori nahi. Okay. Each child gets at least one value. Mane what type of functions are we talking about now? Onto functions. Okay. Each child should get at least one value. That means for each ci here, I should get at least one value from there. Okay. So then the problem becomes difficult. That is actually the number of onto functions from a set having 12 elements to a set having 10 elements. Okay. So these things are there in combinatorics. So if video mode if you are interested, you will see that. Okay. So that is actually inclusion exclusion principle. Okay. Nothing but this one. Okay. Number of elements of a set. Suppose the set this is a universal set and this is A, this is B. Okay. What is the number of elements of A complement intersection B complement? Number of elements of this will be number of elements of S minus S is the universal set. Number of elements of A union. Okay. This one. No? Okay. So here number of elements of S minus number of elements of A plus number of elements of B. No? And plus number of elements of a generalization of this inclusion exclusion principle. Okay. This is for two sets. There you have to work with n sets. Okay, so something like that. So it's not there in your course, but earlier it was there in earlier syllabus, non-CBCS syllabus. It was there in 6th semester. 6th semester inclusion exclusion principle. In those syllabus I tried very much to include this, but unfortunately it was not included. Combinatorics became a special paper, optional paper, so that will not be taught most probably. Okay. So এগুলো প্রবলেম বেশিরভাগ এর মধ্যে আসে, অলিম্পিয়াড এক্সামস এর মধ্যে আসে, অলিম্পিয়াড এক্সামস। Okay. So at least you know how many functions you can define from a set having m elements to a set having m elements. Okay, this is very simple. M to the power n. Number of onto function, one function is factorial n divided by factorial n minus n. Okay. This to know. So if a set A and B have the same number of elements, how many one functions you can define? How many bijections or one functions you can define from here to here? Huh? Okay, I have already said, no? If both have n elements, factorial n. Factorial n divided by factorial of n minus n. That is actually factorial n by factorial 0. So from a set to itself, you can define exactly factorial n one functions. Okay. So if a set has only 5 elements, a1, a2 up to a5, okay, then you can define 120 functions. Okay. 120 functions you can define. Okay. If a set has 6 elements, you can define much more, 720. Okay. Shorter element is 5040. Okay. Factorials are very large numbers. So there is no scarcity of one function. Only one function is there. Lots of one functions are there. Any permutation is a one function or arekta naam holega one on two function. Another name is permutation. Okay. Bijection from a set to itself. Okay. Another name is permutation. Okay. Because when you take bijection from a set to itself, what we are doing is we are just changing the order of the elements. Which is 1 2 3 to 1 2 3. If I define a bijection, something like this, 1 goes to 2, 2 goes to 1, 3 goes to 3. Okay. So this is actually a permutation of this elements 1 2 3. 1 is going to 2, 2 is going to 1, and 3 is going to 3. Okay. This is actually just a rearrangement of the original elements. Okay. So that is why a function from a set to itself, which is a bijection, it is also called a permutation. Okay. So the set may be finite or infinite. Any bijection from a set to itself is called a permutation. This is just a DNA. These are various ways of looking at functions. Okay. এটা করলাম ইনভার্সটা করলাম। ওকে। Okay, so let us try this, find out the inverse. Let's do it. Okay, and so exercise is this, the inverse of this function, f inverse from y to x. X is f from x to y. Okay. That is f inverse whole inverse. Okay. This is same as that. Okay. This also follows from the definition. We'll just write a few lines. Okay. We'll just write a few lines. So before this, we will do another exercise. Let f from x to y be a bijection. Then f inverse from y to x. Okay, this is also a bijection. This is also a bijection. F from x to y is a bijection. If you consider the inverse map, that is also a bijection. So let us try this. F from x to y is a bijection. Then f inverse from y to x is also a bijection. One map. Right. So first of all, let us see whether it is 1 or not. So solution is, so let x, so we'll start with two different elements from y. Let y1, y2 belongs to capital Y be in the elements such that f inverse y1 equal to f inverse of y2. So equal to x, say f inverse of y1 is equal to f inverse of y2. Okay. So we can take f inverse of y1 equal to f inverse of y2 equal to x, where x belongs to capital X. Okay. Because f inverse is a function from y to x. Okay. So f inverse y1 is equal to f inverse y2. It will be an element of x. Okay. Capital X. So we can take it as small x. Right. So what do we have? Therefore we have f inverse of y1 is equal to x. Okay. And f inverse of y2, this is also equal to x. So by definition of inverse, by definition of inverse, if inverse y1 is x, this will mean that f of x is y1. Okay. And f inverse y2 is x. So the definition says that this will happen only when fx is y2. Right. Just we are applying the definition. The definition says that whenever you have something like fx equal to y, then f inverse of y will be x. So here we have f inverse of y1 is x. So that means fx was actually y1. Okay, that This is why f inverse y1 is. Okay, so from here what is your conclusion? Fx is y1 also, fx is y2 also. So y1 is equal to y2. Okay. So from this line I can write, this implies y1 is equal to y2. Okay, so f inverse is 1 1. Therefore f inverse is 1 1. F inverse is 1 1. So one part I have shown. I have shown that f inverse is also 1 1. Okay. Next I have to show that f inverse is on 1. To show f inverse is on 1. Just वही definition टा गुड़ाई में सही है तो लिखा है. Now let to show f inverse is on 2 I have to take an element from capital X. Now let x belongs to capital X be any element. Be any element. Okay. Then since f is a function from x to y, since f from x to y is a map, so fx will be an element of y. Fx belongs to capital Y. Okay. Fx is an element of capital Y. So let us denote that fx by small y. So let y is equal to fx. Let f of x equal to y, where y is an element in. Okay, fx is an element of y. So fx will be, we denote fx by small y. Okay. So by definition again, so we have an element x which satisfies fx equal to y. So by definition of inverse, we have f inverse y. Okay. So for any element in the codomain, we have got an element y in the domain for which f inverse y is. So therefore, f inverse is on. So f inverse is also a bijection. So whenever f is a bijection, f inverse is a bijection. Thus, f inverse is a bijection. Okay, so inverse of a bijection is also a bijection. Okay. So the problem may be something like this. Show that, or the question may be something like this. Show that the inverse of a bijection is a bijection. So you can just write this argument. Okay.